Bayesian spatial statistics is the study of statistics where data has location information included in the data itself. Some of the research questions we're looking to answer are identifying the bound of an object in an image. We're also trying to use different cell information to ascertain whether or not we think there is sort of human activity in a certain region to dig for archaeology. And we're just going to, in general, be thinking about trying to find more information about location and using this location information to find more about the data. A basic example is trying to find the bound of this coffee lid in the overall image itself. So we want to classify each pixel in this image as either a part of the coffee lid or not a part of the coffee lid. So figure 1 is the original image, and first we need to find an initial set of values for the Gibbs sampler. So we just do a simple threshold above which the brightness of the pixel is classified as part of the image and below which it is not a part of the image. This is really rough, so we definitely want to use a Gibbs sampler to refine the bound. And in figure 3 we have, after sort of an initial Gibbs sampler, this is what this looks like, the bound. We're going to refine this later so that it looks a little bit better. But what you should notice about this image is that, one, the image, the bound, and the Gibbs sampler have had their resolutions reduced from the original image. And that's important because that saves the amount of time that we're going to be doing computations for. When you increase it to the original image resolution, it can take substantially longer, though we will be doing that later. And the other thing to notice is that the bound is extremely rough, and we're going to think about the kinds of things we can do to refine that bound to be a little bit smoother. The basic idea behind running this, running the bound, is that we have each pixel and then we take a certain neighborhood radius of surrounding pixels and run our Bayesian methods on that. If we ran it on the entire subset of pixels, so if we had this purple pixel as the center pixel, and we ran it on all of the pixels in this sort of rudimentary image, then it would take a very long time because we'd be running it on however many pixels we have in our image, and we'd be running that for each pixel. So instead we do this thing where we take a neighborhood, and in this case it's a neighborhood of r equals 1, but we're going to be looking at different neighborhoods later, and run the algorithms on that. The model is pretty simple. We create a matrix called X, which is either 0 or 1, and that is the classification of the object in the image as either part of the object or not part of the object. And then we have our matrix of Y's, which are the image information, and we convert it to grayscale, so any given pixel is just between 0 and 255. And we want to determine which likelihood is greater, whether the likelihood of any given pixel being a part of the image is greater or not part of the object is greater. So the likelihood function we use in this application is the sort of sum of the product of the similarity function and the same, what we call like function, the delta function. What happens here is we simply multiply, or we add up whether or not any two pixels are similar in the radius. So if you have your center pixel and then you have a radius of 1 around it, we're going to sum for each of the pixels surrounding the center pixel whether or not they're similar, and if they are similar we add 1, if they're not similar we subtract 1. And then we do that for xt is equal to 1 or negative 1. And then we find 1 or 0, and we find which one is greater. And if 1 is greater, then we flip the pixel to 1, and if the 0 is greater, then let's say the pixel remains 0. So now we've seen 3 different parameters that we can adjust. The first parameter is the radius of the neighborhood. In the examples past, we've seen a radius of 1, but we can push that to 2 or 3. The only downside of this is that with the radius going up, the number of cells that we're running the sampler on, it goes up exponentially. So if the radius is 1, we're only running it on 8 surrounding pixels. if the radius is 2, we're running it on 15 surrounding pixels, and so on. The next parameter is image resolution. We can reduce the resolution, which allows us to run it on fewer pixels, but then the bound is going to be a little bit rougher. And lastly, we can run it on color. Since we're converting it to grayscale in the previous examples, it means that we're losing a lot of information. 2 pixels might have the same grayscale color, but when we add it into the vector of 3 colors, they can be pretty substantially different. So running the similarity function on a colored image has the potential to differentiate much better between 2 pixels. And here's the resulting example of running it with sort of different parameters. In the figure 4, we have what we had before in the original example, which is a similarity function of a simple 20 difference, which means if 2 pixels are more than 20 in brightness apart, then we say they're dissimilar, and if they're less than 20, then they are similar. And this is with a radius of 2 around each pixel, and it only takes 10 Gibbs samplers, which becomes a little bit more important when we look at the higher resolution example. In figure 5, we have the same other things, except we change the similarity function to 30 different, and you can see that the bound becomes significantly cleaner. And then lastly, we have the image converted to a higher resolution. For this one, the bound is a little bit rough, because we also do use the image similarity of 30 different, but the bound is a little bit rough still. But what you'll notice is that we have a lot more clarity in the image due to using the high resolution, but it also took 250 Gibbs samplers instead of only 10. And we'll see that in the next slide, why this is. So you can see in this time lapse how exactly the Gibbs sampler works. Basically, the border grows because any given pixel finds out more information about the pixels around it as the border grows inwards. So if we have a pixel that is in the white region and pixels are surrounding it that are part of the black region, then it'll be able to more readily change to being a part of the object. But if it's in a zone of completely non-classified pixels, then we sort of end up with a situation where it takes more effort to flip the pixel. It means that all the pixels around it have to be completely dissimilar to it for it to flip. So there's a couple limitations here. One is that we can't recognize 3 objects in an image. We're using a binary classification. And why we can't sort of do 3 objects is because the initial classification is pretty naive. And the only reason why we end up with this classification in the end is that the initial classification is close enough to the original image that it sort of recognizes pixels around it. So doing 3 objects would be a little bit more difficult because we can't just do this binary good classification. We'd sort of have to go in and manually create a rough bound for each of the 3, and even then you sort of end up with this weird situation where it would be overlapping bounds have the capacity to sort of misclassify an image, in our opinion, would be misclassification. And it is possible to classify patterns, but that doesn't use a similarity function between 2 pixels. It uses a similarity function between the entire neighborhood. But in the next example, the next application, we're going to be doing something a little bit different, but still sort of in the same vein. So for application 2, we're looking at human activity in this archaeology site using phosphate measurements. The data looks like this. We have some missing values, which are represented by pluses, and the rest of it is just these phosphate concentrations, higher concentrations corresponding to a higher likelihood, essentially, of human activity. And these are taken at 10-meter intervals, these measurements. The model is a little bit deeper this time, and it also will allow us to look at a posterior probability of any given cell being either indicating human activity or not. But basically it has the same idea as the previous model, which has to do with counting the number of similar pixels around it, meaning that allowing for pixels that have a lot of similar pixels around them will be more likely to correspond to that pixel. because human activity is going to happen in groups. So this is what our N classification looks like. You can see that there's these sort of two regions where we think that there is human activity, and that's where we would recommend they dig. And this corresponds to these a little bit hard to see bolded values. We sort of just take a threshold of 50. If it's above 50, we say, okay, this is where human activity could have happened. But this is useful because if we're sort of recommending to an archaeologist where to dig, we can say, here are the possible regions, and here's the likelihood or the probability that we think the human activity previously occurred in those locations. So what's useful about this methodology versus the previous sort of similarity function is that we're actually able to draw a posterior probability, but since this image is only technically 16 by 16 and the other one was substantially larger, this actually takes more time. So if we're trying to be more accurate with these posterior probabilities, then we have to make sure that we either have enough computation power or that we can just use the other application and not be as sure. And it's the same sort of idea of further research, which is if we want to if we want to use more data to classify more location information, then it's important that we are trying to find a way to do multiple classifications. And that's it.